Hello, this is ISSMGE Webinar 2020 on the topic of the synthetic reinforced soil structures, developments from walls to bridges. I am Tatsuoka. This is abstract. You may read this later. The contents. The first is the recent typical GR structures for railways in Japan. Second is inextensible versus extensive reinforcement and stiff versus flexible facing. Third is insight into the roles of full-height rigid facing. Fourth is the advantages of stage construction of full-height rigid facing. Fifth is GR's bridge abutment and GR's internal bridge. Sixth is the collapse of soil structures by earthquakes, floods, and tsunami, and restoration to GRS structures. Concluded remarks. First topic is recent typical GRS structures for railways in Japan. GRS is the synthetic reinforced soil. This is Shinkansen, high-speed railway network in Japan. Black and white lines are the lines in service, and the red lines are the lines under construction. So the right-hand side, Hokkaido Shinkansen, and part of this was opened March 2016. The remaining part is under construction. This is a Mantaro site of this Hokkaido Shinkansen, and R means a GRS retain wall. In total, 3.5 kilometers was constructed. A means GR's bridge abutment. In total, 29 was constructed. And I means GR's internal bridge, not constructed here, but another place. I'll explain. B means the GR's box culvert, and T means GR's tunnel exit protection. So all these were constructed in place of conventional type structures. This is a close view of GRS tunnel entrance exit protection and GRS retain wall with full height rigid facing and GRS box culvert. This is GRS bridge abutment, and first is the shallow ground improvement is made when necessary. Second, the grid reinforced soil wall is constructed. Three is reinforced backfill. At this stage, no reinforced concrete. Then the full height rigid facing is constructed, firmly connected to the grid layers. The fifth is girder bearings or shoes. Then sixth, a simple girder is placed. So next is the left-hand side, Kyushu Shinkansen Nagasaki route. This is under construction. This is the list of GRS structures for Kyushu Shinkansen Nagasaki route. GRS retain wall in total 5 kilometers. GRS tunnel entrance exit protection is 55. This is 89% of total number of this structure. GRS bridge abutment in total 80. This is 100% of the all bridge abutments. And GR's internal bridge 7. So these GR structures are constructed much more densely than Hokkaido Shinkansen. This is showing a GR's retain wall for Omura Rail Yard. So this is showing a GRS bridge abutment. And step 1 is a bench cutting of natural slope. Step 2 is a construction of approach field. That is a zero-grit reinforced, well-compacted, lightly cemented mixed gravel soil. Third step is a soil compaction, at least 95% of the maximum dry density at the optimal water content by modified Proctor. Fourth step is arrangement of zero-grit layer, and fifth step is completing the approach field. Sixth is completing GRS bridge abutment by constructing flow-height ridge facing. This is GRS tunnel entrance exit protection. This is showing the structure of GRS tunnel entrance exit protection. The bottom left is one is a backfill compaction. 2 is showing the arrangement of the grid layer. 3 is showing an intermediate stage before the construction of flow-height rigid facing. This is showing the GRS integral bridge constructed at Genshu. The first step is excavation of subsoil. The second step is construction of approach fields. So this is the grit reinforced, well-compacted, lightly cement mixed gravel soil. The back is the unreinforced backfill. The third step is the construction of RC facing after sufficient deformation of the embankment and the subsoil has taken place. Then the fourth step is the arrangement of PC girders. Then the fifth step is a structural integration of the girders to the flow-height rigid facing. Then construction of slab and others to complete the bridge. So this is a completed GRS internal bridge at Genshu. So you can see the GRS tunnel entrance exit protection and RC slab track. We are using a continuous RC slab track for high-speed railways. This is compared to the conventional ballast track. RC slab track needs relatively high construction cost, but it largely reduces maintenance cost. So this is becoming the standard track structure for Shinkansen. So due to very small allowable settlement of subsoil, this is not constructed on conventional embankments, but this is constructed on GRS structures without problems. This is showing construction sites of GRS retaining walls with full height ridge facing and the related other GRS structures as of June 2019. The total wall length is 184 km. The total number of the project sites GRS retaining wall is more than 1,200, and GRS bridge abutment at 39 sites, and GRS internal bridge is at 8 sites. We had no problematic case during and after construction in all projects. This is showing the history of GRS structures. The research was started at University of Tokyo from 1982 and at Railway Technical Research Institute from 1987. The vertical lines are showing the wall constructed annually, and the red curve is showing the total wall length, which leads to 184 km. 1995, we had a Kobe earthquake. So in year of 2000, we restarted the construction of new Shinkansen lines. 2004, we had a Niigata-Kenchiuchi earthquake, and 2011, we had a Great East Japan earthquake. So there are a couple of events, many events, which are very important factors to develop this technology. Summary: GRS structures with full-height rigid facing have become the standard railway structures in Japan, constructed basically in place of conventional type embankments, retaining walls, bridge abutments, and bridge systems. This is due to, compared with conventional type structures, higher performance under long-term ordinary conditions and against earthquakes, heavy prolonged rainfalls, floods, and tsunami, and lower cost for construction and long-term maintenance. Next, several theoretical and technical issues that we coped with when developing these GRS technologies for the last nearly 40 years. Next topic is the extensible versus extensible reinforcement and stiff versus flexible facing. There are two types of facing. One is flexible, not developing high earth pressure on the facing. The other is a stiff facing, developing high earth pressure on the facing. There are two types of reinforcement. The first one is inextensible, typically a metallic strip, and the other is extensible, typically a polymer and planar, that is the grid. For example, the grid. The combination of two factors, we have different types of GRS retaining wall. A, using a metallic skin facing. B, using a discrete concrete panel facing. C, wrap-around facing. D, modular block facing. And E, full-height rigid facing. So A and B are using inextensible reinforcement. C, D, E are using extensible reinforcement, typically the grid. Previously, many considered that facing is only to prevent the spilling out of backfill, and the large earth pressure does not develop at the back face of the facing. However, we consistently observed that large earth pressure develops at the back face of stiff facing that is firmly connected to the reinforcement layers. For example, B, D, and E. And when facing is sufficiently stiff, the reinforced soil exhibits small deformation and high stability. This is a case reported by Schlosser 1990. This is discrete panel facing for metallic strip reinforced sand retaining walls. We can see relatively high tensile forces at the connection of reinforcement to the discrete panel facing. That is, relatively high earth pressure on the back of the facing. This is another case, so discrete panel facing for the textile reinforced clay retaining wall. We can also see the relatively high tensile forces at the connection of reinforcement to the discrete panel facing, that is, relatively high earth pressure on the back of facing. This is Chiba number 3 test embankment. I will explain later. So similar trends were observed in a number of reinforced soil walls having relatively stiff facing. So the previously many considered that to achieve small wall deformation and high wall stability, inextensive reinforcement is necessary and flexible facing is sufficient. However, we often observe that relatively large wall deformation when using a flexible facing despite the use of inextensible reinforcement, for example A, and a small wall deformation when using a stiff facing despite the use of extensible reinforcement, for example D and E. These observations indicate the paramount importance of using stiff and durable facing. This is a fact I did not recognize in the beginning of 1980s. In the 1980s, we constructed 5 full-scale test embankments, step by step improving the structure of facing from wrap-around to finally full height rigid facing. As shown in the following, from the performance of the 5 test embankments, we learned that first, the wall deformation can be made small enough by using a full height rigid facing despite the use of so-called extensive reinforcement, that is, their synthetic reinforcement, including their grit. Second, full height rigid facing is durable and aesthetically acceptable. This is showing Chiba Experiment Station, Institute of Industrial Science, University of Tokyo. I was living here in this apartment. The left top is a second test embankment. So we constructed in total 3 here. This is showing a Chiba number 1 embankment of clay backfill, constructed in 1980s to examine whether stable reinforcement clay walls can be constructed. A non-woven geotextile, which is usually used as a drain material but not as reinforcement due to very low tensile stiffness. And we made a flat wrapped around wall facing like this. The wrapped around facing exhibited large deformation already during construction and more by reinforced after construction, while not durable and vulnerable to ultraviolet light. So we can conclude that this wall facing or wall face is not relevant to important permanent walls. So this is the right bottom is showing the mechanism of large compression and settlement of the backfill. First is a softening of soil by wetting, by rainfall. Second is the compression of the backfill. Then third is a decrease in earth pressure due to rounding of the facing. Then again the compression. Then the decrease in earth pressure. This is repeated. Finally, we have a large settlement like this. This is Chiba number 2 embankment of clay backfill. This was constructed in 1984 to examine whether the wall becomes stable by placing a soil box at the shoulder of each soil layer like this. This was slightly larger than Chiba number 1, and clay backfill and non-woven geotextile were used as Chiba number 1. You can see a box placed at the shoulder of each soil layer. These bags were filled with clay backfill. By using soil bags, we observed good compaction and good confinement, leading to high strength and stiffness of the backfill near the wall face, resulting in a very small long-term deformation as shown in this figure, and stable behavior in a heavy rainfall test, supplying 70 cubic meter of water for 8 days from the crest. This is a cross-section which was demolished when demolishing the test field. Chiba number 3 embankment of clay backfill. This was constructed in 1986 using a clay backfill and non-woven textile as number 1 and 2 to evaluate the effects of facing type on the wall stability. 3 facing types are A, the left side one, wrap around with flexible geotextile seat without using soil bags. B, the right hand side, the discrete concrete panel without using soil bags. And C, the center, at the center, wrapped around with sandbags covered with a 8 cm thick shotcrete. A, wrap around wall face with flexible geotextile seat without sandbags exhibited very large deformation again. B, discrete concrete panel facing without soil bags. This exhibited much smaller deformation than a wrap-around facing without soil bags, but not small enough, and very difficult to compact soil immediately behind the panels, maintaining a good wall face alignment. C, wrap-around facing with soil bags covered with shotcrete. This shows much better constructability than B, discrete panel facing, and much smaller deformation than a wrapped-around facing without soil bags. However, the wall deformation is not small enough, while the wall face is not aesthetically acceptable to be used as important permanent structures. So this issue, underlined here, we expected that these problems can be solved by using a full-height ridge facing. To ensure the above, 2 more test embankments were constructed. This is showing 2 test embankments constructed at Railway Technical Research Institute. The right-hand one is a JR number 1 sand backfill, 5 meter high, using a geogrid. The wall face is already completed with full height ridge facing. The left-hand side is a JR number 2 clay backfill, and the wall face is before construction of full height ridge facing. This is showing the behavior of JR number 1 with sand backfill. These are showing behavior for 2 years after completion of 2 types of facing, all using gravel bags connected to the grid layers. Segment H, using a discrete panel facing, exhibited a relatively large deformation, you can see here. The other segments use a full height ridge facing, all exhibited very small deformation. We performed loading tests using a footing placed on the top of the embankment. This is showing a front view of test segments H, F, D. These wall segments were brought to failure by using this footing. So this is showing a cross-section of segment H, which was exposed by excavation after test. The footing has been removed, and we observed the failure planes at the wall face. Here the sandbags, and facing is a discrete panel facing. Segment H with a discrete panel facing, and the grid length was 2 meters. The facing backward, as shown here by the letter B, and we observed the largest wall deformation shown in this figure, the relationship between average footing pressure Q and the lateral outward displacement at the top of the facing delta. Segment F, using a full height ridge facing, and the length of the grid is only 1.5 meters. This was more stable than segment H despite shorter the grid. Segment D, the right-hand one, D. This used a full height ridge facing, and the length of the grid was 2 meters. This was more stable than segment F due to longer the grid, and much more stable than segment H by using a full height ridge facing. However, stability of segments F and D was controlled by yielding of construction joint, denoted by Cj. In the facing, which was not steel reinforced. The full height ridge facing for prototype GRS retain walls constructed afterwards for railways are always lightly steel reinforced. The lessons learned from the behavior of 5 full-scale model. First, when the facing is flexible, or when stiff facing is not connected to reinforcement, we have small or no earth pressure at the wall face, which results in low tensile forces in the reinforcement, in particular at low elevations. Then, in active zone, low confined pressure, therefore low strength and stiffness of the backfill. Then we have a low stability of the wall. When the full height rigid facing is firmly connected to reinforcement, then we have a high earth pressure at the wall face, then the high tensile forces in the reinforcement. As a result, in the active zone, high confined pressure, therefore high strength and stiffness of the backfill, then we have a high stability of the wall. The wall deformation can be made small enough by using a stiff facing even when using the so-called extensible reinforcement, that is, the synthetic reinforcement, such as the grid. Full height ridge facing is a good solution also for durability and aesthetics. Next is the insight into the roles of full height rigid facing. This is showing a conventional retain wall. This is a cantilever structure. As a result, we have large forces in the facing, and we have a large overturning moment and large lateral load at the facing base. Then we need a massive strong facing structure and a pile foundation. Yet this wall type is relatively unstable, particularly against seismic loads. This is showing a collapse of gravity-type retain walls during 1995 Kobe earthquake. These retain walls were designed against seismic loads, yet you can see overturning failure. So two types of retain walls were used for highway in Yamagata. This is the conventional retain wall. This was previously constructed. This is cantilever retain wall, so therefore they constructed a large diameter board piles and used RC anchorage. they changed the wall type to a GRS retaining wall with full height ridge facing. So this was newly constructed in 1995. They didn't use a large diameter power hose, and they didn't use RC anchorage. So you can see full height facing is much thinner than cantilever RC retaining walls. So the cantilever RC retaining walls was constructed like this. Then at that moment, GRS retaining walls was under construction. So the left bottom is a wall during construction, and the right hand side figure is showing a GRS retaining wall with full height ridge facing that had been completed. This is showing two basic force equilibriums with reinforced soil walls. A, along the potential active failure plane. Along this line, tensile forces in reinforcement is in equilibrium with the active earth pressure, P sub A. This stress equilibrium is always considered in design. So this shows that GRS retaining wall is not a cantilever structure. We have the other force equilibrium, that is B at the facing. This is very important but often ignored. So this implies a paramount importance of facing rigidity and connection strength. Again, with this force equilibrium, GRS retaining wall is not a cantilever structure. I'm going to explain the equilibrium B. GRS retaining wall with full height ridge facing is now, with this retaining wall, full height ridge facing is a continuous beam supported by many reinforcement layers at a small span. As a result, we have very small forces in the facing, which results in a simple facing structure. In addition, we have a small overturning moment and lateral force at the facing base, which results in no need for pile foundation, and the wall becomes stable, particularly against seismic loads. This is a GRS retaining wall with full height ridge facing, which was constructed in 1992. I took this picture immediately after completion. I took this picture a week after the 1995 Kobe earthquake, so the wall survived. So many Japanese wooden houses were totally collapsed by this very strong seismic load. So we performed a series of shaking table tests to simulating these retaining walls. First is the gravity-tied retaining wall, which collapsed. The other one is a GRS retaining wall with full height ridge facing. The reinforcement layer, 10 layers, is very short. L by H is only 0.4. This was designed by the old code using a low KH equals 0.2. Exceptional with this wall, all reinforcement layers are very short, L by H equals 0.4, due to specific space restriction at the site. This is the result of a shaking table test. The actual seismic acceleration record was used as an input acceleration. Maximum acceleration is denoted as A max. The A max by G is seismic coefficient KH, and the wall top displacement D top is plotted against KH. The gravity type retaining wall shows a large displacement. Compared to that, the displacement of GR's retaining wall. This time, this is denoted by R1. So the displacement of R1 is much smaller. Yet, this is not very satisfactory. So, to evaluate or examine the stability of different types of retaining wall, we performed also, in addition to G, gravity type, and L is a leading type, and C is cantilever. G, C, L is a conventional type. All these show a very similar large displacements. R1, R2, R3 are all GRS retaining wall. R1 is the model of the actual retaining wall. R2, the two layers of reinforcement were made longer. R3, all reinforcement layers has the same length with L by H equal 0.7. So compared to a similar unstable behavior of GLC, now R1, R2, R3 are more stable, and particularly with R2 or R3 are very stable. R2, now this is more stable than R1 and similar behavior as R3, while more cost-effective than R3 because of a less amount of the grid. And this is an important point, a less amount of excavation required to construct a GRS retaining wall on an existing slope. The bottom or the reinforcement at low levels are very short. So now the arrangement is adopted and specified in the current design code. This is showing that the use of short reinforcement layers at low elevations reduces the slope excavation, but it decreases the wall stability. However, the use of several long reinforcement layers at high elevations, together with a full height facing, ensures small shear deformation and high stability against overturning moment and lateral sliding, particularly against surging loads, and the stability against concentric loads near the wall face at the crest, as shown in this figure. To create new space on the slope, typically in the urban area, we often use this conventional method: seat piles, anchor, excavation, pile, cantilever RC retaining wall, finally backfilling. As a new method, we also use reinforced slope retaining wall, in this case with long reinforcement. This is more cost-effective than the conventional method. However, in both cases, large slope excavation and temporary anchored seat piles are required, which is costly. On the other hand, GRS retaining wall with full height rigid facing, we have short zero-grid layers at low elevation and long zero-grid layers at high elevation, and the use of full height rigid facing. Then we have small slope excavation and no anchored seat piles, while stable wall behavior. Then this method becomes much more cost-effective and a short construction period required. This is showing a typical design by the current code and guideline. So the allowable minimum length of the basic zero-grid layers is the largest value among the following three values. First is at the 35% of wall height, second is 1.5 meter, and the length required for a sufficient stability against overturning, lateral sliding, and shear deformation determined by stability analysis. So we are using a two-wedge stability analysis. This is the general case. In this case, stability is examined for all possible locations of point A and B and all possible angles theta A and theta B. With the full height rigid facing, point A is located always at the bottom of the back of the facing. This makes the wall very stable than general cases. We also have a three-dimensional effects of full height rigid facing. That is, each GRS wall section between construction joints behaves monolithically. That means local failure is very difficult to take place and to develop toward overall collapse. And full height rigid facing can support external loads V and H caused by electrical supply poles, noise barrier, crash barrier, and bridge girder as shown in the two bottom figures. These are conventional return walls and RZ viaduct. Their disadvantage is that they are costly, but their advantages are limited occupied space and facing supports other structures. GRS return walls with deformable facing, their advantage is that a higher cost effectiveness, but the facing cannot effectively support other superstructures. As a result, we need a buffer zone like this. In comparison, GR's return wall with full height facing, the advantage is a higher cost effectiveness, and facing can effectively support other superstructures, and now a buffer zone is unnecessary. This is a typical case. You can see the trains running very close to the wall face. This is another case of GRS return wall with full height rigid facing, supporting a very busy urban railways. You can see a train is running very close to wall face. The function of the facing summary. First, the facing is the important and essential structural component that confines the backfill, develops large tensile forces in the reinforcement, and supports other structures, so the facing should be rigid enough during service. Second, on the other hand, the facing should be deformable enough to accommodate the deformation of the backfill and supporting ground during wall construction. These are contradicting to each other. This contradiction can be solved by staged construction. Next is the advantage of staged construction of full height rigid facing. If full height rigid facing is constructed before the construction of the backfill, we have several problems during and after wall construction. We need a propping, and we will have a large load. It is difficult to compact the backfill immediately behind the facing. The connection may be damaged by relative settlement between the facing and backfill. And tensile strains do not develop before removing the propping. And upon the removal of the propping, uncontrolled movement will take place. So these problems can be solved by staged construction procedure. This is a typical case for Shinkansen yard. This picture is showing the site before the start of construction. This picture is showing a completed wall before constructing full height rigid facing. This is a completed wall with a full height rigid facing. So this is a cross view of the wall. This is a reconstruction of a gentle slope to a vertical wall for a yard of Shinkansen at Biwajima, Nagoya. This is showing the details of stage construction. Step 1 and step 2. Construction with the help of gravel bags placed at the shoulders of its soil layers. Step 3, backfilling and compaction, and this procedure is repeated. Good compaction of the backfill can be achieved by a small lift, 15 cm, resulting from a small vertical spacing, 30 cm, of the grid layers, and there is no rigid facing during backfill compaction, like this. Step 5. Now the wall is completed, but the full height rigid facing is not yet constructed. From step 5 to step 6, after sufficient compression of backfill and subsoil has taken place, a full height rigid facing is constructed by casting in place fresh concrete directly on the wrapped around wall. Actually, the fresh concrete is cast in place between concrete form and the wrapped around wall face. In this way, fresh concrete enters the gravel bags through the aperture of the grid bags, which resulting that the facing and the grid reinforcement are firmly connected to each other. This connection strength was examined. This full-scale test and laboratory test on the connection strength. The left side part figure is showing a field test. That test specimen was cut out from the full-scale facing and hung under 1G, so no separation took place. In the laboratory, the separation test was performed. In this case, this typical split test, the largest split stress is much higher than the stress, which is equivalent to inertia of 2 meter thick facing under 1G. Actually, the ordinary facing thickness is 0.3 meter. So this is actually a very large separation load. This is step 6. Wall is complete. Now back to the from step 5 to step 6. After step 6, the differential settlement between the facing, flat rigid facing, and the backfill becomes very small. As a result, the facing zero grid connection is not damaged during service of completed wall. This means construction using compressive backfill and or on a compressive subsoil becomes possible. This is a typical case showing that point, Nagano wall for yard for Shinkansen. The backfill was nearly saturated soft clay. The wall was constructed on a thick, 30-meter thick, very soft clay deposit. So no pile foundation was used. The stage construction was as follows. First, 3R slating wall without rigid facing was constructed, and the second is a preload fill was constructed. Third is the settlement of about 1 meter took place. Fourth is a removal or preload fill. Then finally, the construction of fluoride ridge facing. This is showing the picture during preloading. Before preloading, the wall height was 3 meters, and that became 2 meters after preloading. So then the construction of fluoride ridge facing was made after removing the preload fill. I took this picture 20 years after construction. Then the wall has been used without any problem. So another example showing the advantage of stage construction of fluoride ridge facing is the construction of box culvert. So this is the conventional method. The piles, the RC box culvert, the embankment, the problem starts. We have settlement and compression of the backfill. That means settlement at the crest of the embankment. This results in a bump. Then we have a load concentration to the culvert, and we have a negative friction. Then the problem of train running. So this problem can be used by using a GRS box culvert. This is a solution by staged construction of GRS box culvert. First, the shallow ground improvement. Second is the construction of zero grit reinforced embankment. Then we will have a settlement of the ground and compression of the backfill. Then we construct GRS culvert connected to the layers and backfilling. Then we have no serious problem with bumping for train running. The next topic is the GRS bridge abutment and the GRS integral bridge. This is showing the story of the development from conventional simple girder bridge toward GRS bridge abutment and GRS integral bridge. We start with the several serious problems with the conventional simple girder bridge. We have a number of problems with conventional bridge abutments. We construct first piles, then RC abutment, then backfill. The problem starts. The earth pressure displaces the RC abutment. We may have a negative friction and bending of the piles by ground movement due to the weight of the backfill, settlement, and lateral flow. Then the bearings. This is also problematic. High cost for construction and long-term maintenance. And we may have a long-term settlement in the backfill. And more problems by seismic loads is the movement of the RC abutment, and bearings have a low seismic stability, and we may have a settlement by seismic loads in the backfill. What is the solution? To solve structure problems, integral bridge has been developed. This is constructed in this way: piles are facing and continuous girder, the integration, then backfill. Many have been constructed in the United Kingdom and the United States due to low construction and maintenance costs resulting from A, no use of girder bearings, and B, continuous girder, use of continuous girder. However, we have several unsolved old problems which is by earth pressure and ground settlement and lateral flow by the weight of backfill, and long-term service issues, A, gradual settlement in the backfill, and B, sudden large settlement by seismic loads. And new problems. We have a seasonal thermal expansion and contraction of the girder, which result in the cyclic lateral displacements at the top of the RC facing. This results in a settlement and increase in the earth pressure. These two phenomena are due to dual ratchet mechanism, which I'm going to explain. This is a static lateral cyclic loading test in the laboratory, and the top of the facing or abutment is cyclically displaced. So this is a sandbox under plane strain conditions. This is a typical result. Lateral displacement of the facing, small d by h, is plotted against elapsed time. The amplitude is d large d by h is only 0.6%. By this cyclic displacement, the total earth pressure coefficient K increases from 0.5 up toward a very high value, nearly 4. And this cyclic displacement of the facing results in a large settlement in the backfill, as shown in this figure. You can see settlement S sub G at a 5 centimeter back of the facing became about 2%. So we have active failure in unreinforced backfill by small cycle lateral displacements of the facing. In this case, only d by h is 0.2%. So active shear band and active sliding took place. Why? This is due to dual ratchet mechanism. With the active displacement of the facing S2A1, we have a formation of active edge and no major deformation and displacement outside the active edge. Next step from A1 to P1. So by this passive displacement of the facing, active edge deforms and displaces as part of the passive edge, but not recovering the active deformation and displacement which took place during S2A1 stage. Then at this stage, we have a formation of passive wedge. Next step C. Now, the second active displacement from P1 to A2. We have a reactivation of active deformation and displacement of the active edge, and no deformation and displacement of the passive edge outside the active edge. From A to P2, the second passive displacement. At this stage, active edge deforms and displaces as part of the passive edge, but not recovering the active deformation and displacement during stage P1 to A2. And the reactivation of passive deformation and the displacement of the passive edge takes place, which increases the earth pressure. Then, to solve the field problems, GRS bridge abutment was proposed. Generation 1, Generation 2. This is GRS bridge abutment first generation. First, the GRS wall is constructed, then the full height rigid facing is constructed, Then girder foundation is placed like this. Then we arrange movable and fixed girder shoes or bearings. Then a simple girder is placed. So we have no bump right back of the full height rigid facing, so which results into low maintenance cost. So stable approach film and high cost effectiveness. This is showing a pair of GRS bridge abutment of first generation, constructed in 1993. We performed a lateral loading test of a girder foundation. The wall showed very stable behavior, stable monolithic behavior. So we observed a satisfactory performance, leading to a construction of many others. However, with long girders, the girder foundation may become unstable by severe seismic load, and their long-term residual settlement may become too large due to inevitable deformation of underlying backfill. This is GR's bridge abutment of second generation. This is constructed in this way. First, GR's wall. Second is full height rigid facing. Third is a girder foundation. Next is the arrangement of movable and fixed bearings. Finally, a simple girder. The girder foundation becomes much more stable by structural integration to the top of the full height rigid facing. So this is much more cost effective and much more stable than conventional type bridge abutment, and this is statically determinate, thus not sensitive to residual displacements of the full height rigid facing. So this is rather simple to design. This is the first GR's bridge abutment, second generation, for Kyushu high-speed railway, Shinkansen. This is showing the field vertical and lateral loading test of full height rigid facing. So blue one is showing the vertical load, red one is showing the lateral load. The left side figure is showing the relationship between lateral load and the lateral displacement of the Pier 5. And the right-hand side figure is showing the relationship between lateral load and lateral displacement of a GRS bridge abutment. We can see that the GRS bridge abutment was much more stable against active lateral load than the combined two piers, very stable. After the construction of the first one at Takada in 2003, shown in the left-hand side picture, by 2018, 36 have been constructed and are in service, and many others are at the design stage or under construction, including 80 for Kyushu Shinkansen Nagasaki route. Yet the following two problems remained when a simple girder is supported by a pair of GRS bridge abutments using bearings, as shown in this figure. The first problem is that there is high cost for construction and maintenance of the bearings, and the second problem is a low seismic stability of the girder at the movable bearing. So, GR's integral bridge that is free from these two problems was developed. GRS integral bridge was developed by combining two technologies, GR's bridge abutment of second generation and integral bridge. GRS integral bridge is constructed in this way. First is the shallow ground improvement when necessary, and GRS always constructed. Full height rigid facing is constructed, and continuous girder is placed, and finally structural integration. We performed a series of laboratory tests to confirm the high performance of GRS integral bridge. In this test, the top of the facing is cyclically displaced. In this case, the backfill is not reinforced. So, by applying a cyclic displacement at the top of the facing, we have a large settlement of the backfill, like this and like this. When the backfill is reinforced, but the reinforcement is not connected to facing, the settlement reduced, but still the residual settlement is very large. When the backfill is reinforced and the reinforcement are connected to facing, now we have nearly no settlement of the backfill. So this is a behavior of GRS integral bridge. We also perform a shaking table test. This is showing a GRS integral bridge model. The model height is 55 centimeter. The length of the girder is 61 centimeter. This is due to the limited size of the sandbox. A mass of 205 km was placed at the center of the girder to make the equivalent length of the girder equal to 2 meters. The table acceleration was uniform 20 waves at a frequency of 5 Hz, and the amplitude was increased step by step. This is showing lateral displacements of the facing in shaking table test. D sub t is a displacement at the top of the facing. This is plotted against the base acceleration alpha sub b. The gravity type shows a large displacement d sub t at the base acceleration of equal to only 200 centimeter per cubic second. And GR's bridge abutment first generation showed large displacement d sub t at alpha b equal to only 400. This is due to this dislodging of the girder. An integral bridge did not show a large dt, but it showed a large displacement at the bottom d sub b at an acceleration of alpha b equal to 600. GRS bridge abutment showed GRS integral bridge showed a much higher stability, but displacement starts at some level, or nearly 1,000 centimeter cubic seconds. We found that the GR's integral bridge becomes more stable by increasing the connection strength between facing and reinforcement. This is showing a settlement in the backfill in the shaking table test. So you can see that the gravity type and integral bridge show the relatively large settlement of the backfill. In comparison, GR's integral bridge did not show a large settlement. This means no bump develops right behind the full height rigid facing, even at so high base acceleration. These are the 4 factors for very high seismic stability of GRS internal bridge. First is a high initial value of natural frequency, C, F0, which is much higher than the predominant frequency of seismic loads. This results in a low initial response acceleration. Second is a slow decrease in F0 by seismic loading, which results in a very slow to reach the resonant state. Third is a large damping ratio. This results in a small response acceleration. The fourth is a high structure strength. All these are by structure integration of the girder, full height ridge facing, and reinforced backfill. About the first and second factors. This is showing test results. With the conventional girder bridge, the initial F0 natural frequency is low, and this natural frequency decreases by very fast with an increase in base acceleration and reach to the 5 Hz equal to input frequency. So this results in a resonance and failure. GRS internal bridge have a high initial F0 natural frequency, and this decreases very slowly with the increase in the base acceleration, and this becomes same as the input frequency only after the base acceleration becomes very high. This is showing the full-scale model of GRS internal bridge, completed 2009 at Railway Technical Research Institute. We performed a lateral cycling loading test, simulating seismic loads and thermal loads. And the model showed a very high stability against such a lateral cycle loads. This is showing the locations of GRS internal bridge which have been constructed until today. First is the GRS internal bridge for Kikonai, at Kikonai, the right-hand side. This is the first one. We can see a slender girder resulting from a structural integration to full height ridge facing and reinforced backfill. So we observed no bump right behind the facing. This substantially reduced the maintenance cost. The second one is 3 GRS internal bridges for Sanrik Railway. This is showing damage to our bridge, typical damage to bridge by tsunami. Over 340 bridges were damaged by Great Tsunami during the 2011 Great East Japan earthquake. And the two weak components of the bridge is first for seismic and tsunami forces. We have two weak components. One is a approach fill. A second is girder bearings. So we propose GRS internal bridge as a solution for these two problems. This is a picture taken 20 days after the 2011 Great East Japan earthquake, and at the Koikurobe for Sanrik Railway. You can see that the girder were washed away by tsunami from Pacific Ocean. This is showing 3 candidates for bridge restoration at Koikurobe. The first one, top one, 2-span simple girder bridge. This is the same as the collapsed one. But the cost is high, and the seismic stability is low, and anti-tsunami stability low. The second one is a single continuous girder bridge with a pair of bearings. So cost is high, and seismic stability is better, intermediate, anti-tsunami stability is low. The bottom one is GRS integral bridge without using bearings. So this is adapted plan. Because of these factors, the cost is low and the seismic stability is high and anti-stability is high. So this is most cost effective with the best performance. This is showing a GR integral bridge at Koikorobe completed in 2014. So the girder is continuous and the central pier is only to support the girder vertically. This is a picture 20 days after the earthquake at Haipe, another place along over Sanrik Railway. At this place, you can see two tunnels. One is railway, the other is road. You can see the all girders are disappeared, washed away by the tsunami from seaside. This is a GRS integral bridge constructed at Haipe. The total span length is 60 meters, and again the central pier is supporting a continuous girder only vertically. 7 GRS integral bridges were constructed or will be constructed for Kyushu Shinkansen. This is a typical one at Genshu as explained in the beginning of my talk. Summary: GRS bridge abutment of second generation supports a simple girder at the top of full height rigid facing of GRS written wall. GRS integral bridge structurally integrates both ends of a continuous girder to the top of the full height rigid facing of a pair of GRS written walls. Compared with the conventional bridge structures, they are much more cost-effective, exhibiting a high long-term stability with no bump right behind the facing and high stability against natural disasters. As a result, they have become standard bridge structures for railways, including Shinkansen. The last topic is the collapse of soil structures by earthquakes, floods, and tsunami and restoration to GR structures. This is a collapse of railway embankments and retaining walls by 1995 Kobe earthquake, restored to GR structures. This is showing collapse of retaining walls by this earthquake. This part was restored to GR structures like this. Another case during 2004 Niigata Kenchu's earthquake. This is showing the collapse of the retaining walls for railway and road. In this figure, the blue one is a structure before collapse. The black thin lines are showing the after collapse. The red one is after restoration. So GRS retaining wall with a full height ridge facing was constructed on this slope. This is the stage construction of full height ridge facing at the site. So left one is a nearly completed wall. The right one is a completed wall. There are a couple of the places where such a collapse took place. Embankment. And this place was reconstructed to GRS retaining wall with a full height ridge facing like this. GRS retaining walls with full height ridge facing for railways, including high-speed railways, had been constructed at many places in the affected area of 2011 Great East Japan earthquake. In total, 95 sites. These had been designed against very high seismic load, and we observed no damage to all GRS retaining walls. These facts validate the current seismic design code for railway retaining walls. So now this is a collapse of railway embankments by floods in 1919, 1993, and 2012, restored to GRS structures. The flood took place in 1990. A small drain pipe crossing the embankment was clogged by flowing timbers. A natural reservoir was formed, and the embankment was fully eroded by overtopping flood. You can see the entrance of the tunnel, and the embankment totally disappeared. So at this place, GRS structures were constructed because of the fast construction, B, only small construction machine necessary at this remote area, and the high stability against heavy rainfall, and low cost for construction and maintenance. This is a picture taken 1994. We have many cases of collapse of retaining wall by scarring, and this is followed by collapse of embankment. So we can expect better performance of GRS retaining wall with full height ridge facing. The scarring in subsoil does not necessarily mean the collapse of the backfill. This is showing a collapse of gravity type seawall for a length of 1.5 km by typhoon number 9, 8 September 2007, close to Tokyo. You can see the gravity type retaining wall collapsed by scarring. So this was restored to GRS retaining wall with full height ridge facing. Like this. The right side is before construction of full height ridge facing. Central part is under construction of full height ridge facing. The left side is a completed wall. So this is the Pacific Ocean. This is showing a collapse of many railway structures by heavy rainfalls and flood in 2013. This is a typical case, collapse of railway embankment by scarring at the 2. This was restored in like this, and this is the stage before the construction of full height ridge face. There, not yet. River is attacking the structure in this way. This is complete GR structures. Now full height ridge facing is working to effectively resist scarring. This is the damage to many railway structures by Great Tsunami. One of the damage is Shimano-Koshi Station. So this is a picture before the earthquake, and this is a picture immediately after 2001 earthquake. And you can see reinforced concrete viaduct collapse by tsunami. Railway track level was 14 meters above the sea level, but the tsunami was higher than by about 8 to 9 meters than the railway track. This is the railway embankment constructed also as a tsunami barrier. The backfill is reinforced with the layers, and the concrete facing are connected to the good layers. So can be very strong against the tsunami over top flowing. Summary: a great number of conventional type retaining walls, embankments, bridge abutments, and bridge system collapsed by recent severe earthquakes, heavy rainfalls, floods, storms, tsunami, etc. Many of them were restored to GRS structures with full height ridge facing because of fast restoration, and second is high stability against natural disasters, even at difficult sites, and low cost for construction and maintenance. Concluding remarks. This is showing a brief history of these GR structures, as explained in some long talk. The fastest embankment this is showing a fastest embankment at the University of Tokyo, clay backfill reinforced with a non-woven textile with a wrapped around wall face. The picture was taken in 1982. These are my two daughters at that time. This is 14 years after the fastest embankment. This is showing a GR's retaining wall with full height ridge facing on an urban railway, Keio line. This is located close to my house. These are my two daughters after 14 years after. 1996. This is 24 years after the fastest embankment. This is a Nagoya GR's retaining wall, 15 years after construction. Now they have husbands. This is 29 years after the fastest embankment. This is the GR's retaining wall with full height facing for an urban railway, Keio line. This is 17 years after the construction. Now families have grown up and there are 3 grandchildren. This is 36 years after the fastest embankment. This is the full-scale model of GR's internal bridge at the Railway Technical Research Institute, 8 years after construction. Now, I had 4 grandchildren. So, GRS retaining walls with a stage constructed full height ridge facing and related GR structures have been constructed as important permanent retaining walls and other soil structures for a total length of about 190 km, many for railways including high-speed railways, Shinkansen. Its popular use is due to high cost effectiveness by high performance during long-term service and against severe earthquakes, heavy rainfalls, etc., and low cost for construction and maintenance. GR's bridge abutment supports one end of a simple girder with a fixed bearing on the top of the full height facing of GR's retaining wall. This is much more cost-effective and much more stable than conventional type abutment. Since open to service, all exhibited practically zero bump. GR's bridge abutment is now one of the standard bridge abutment for railways in Japan. GR's internal bridge structurally integrates both ends of a continuous girder to the top of the full height ridge facing of a pair of GR's retaining wall, not using bearing. This is much more cost-effective and much more stable than conventional simple girder bridge. GR's internal bridge is now one of the standard bridge systems for railways in Japan. A great number of conventional type embankments, retaining walls, and bridges collapsed during severe earthquakes, heavy rainfalls, floods, tsunami, etc. Many of them were restored to GR structures with stage constructed for height rigid facing. The following three breakthroughs were necessary to develop the GRS technologies explained in this presentation. First is that full height rigid facing for changes from low earth pressure to high earth pressure in the wall, and from facing as a secondary non-structural component to a primary structural component for GRS structures. Second is the stage construction for a change in construction from the backfill last to the backfill first. Third is the structural integration of the girder to the full height rigid facing for a change from a statically determinate but unstable conventional soil structures to statically indeterminate but stable GRS structure, in particular GRS internal bridge. So I sincerely appreciate great contributions of all my many students, researchers, and engineers of these organizations. So thank you very much for your kind attentions. The PDF files of the related technical papers of GRS structures by Tatsuoka et al. Can be downloaded from this site. Thank you very much.